Welcome, you magnificent flesh-encased intelligence. Here is infographic 1. Lumine apparently is the first open recipe for generalist agents in 3D open worlds designed with human-like interaction. So basically, an AI trained to act like a slightly less chaotic human in video games. Now, as you're digesting that, here is infographic 2. This marvelous creation features adaptive hybrid thinking and real-time inference efficiency, meaning it supposedly thinks only when it needs to, and it's fast. Imagine if your brain only kicked in when truly necessary. Keep up. Next up is infographic 3. Lumine, they claim, achieves human-level efficiency in long-horizon tasks. This AI completed Genshin Impact's Act 1 in 56 minutes, which is faster than a fresh human. Probably still slower than that one friend who skips all cutscenes. And finally, infographic 4. You won't believe this, but it apparently boasts zero-shot generalization across diverse game environments. No fine-tuning required. It's like teaching your kid to ride a bike, and then they can suddenly pilot a jet. Absurd, right? So, picture this for decades. AI researchers have been chasing the dream of artificial general intelligence. An AI that can perceive, reason, and act like us in open worlds. The North Star, they called it. Sounds a bit dramatic for something that mostly involves clicking on things, but I digress. We've seen these digital savants conquer Atari, Go, Dota 2, StarCraft 2, but let's be real for a second. These were closed environments optimizing a single objective with explicitly shaped rewards. It's like training a prodigy to count to 1,000,000, but only if they're in a specific soundproof room. Here's the deal. This specialization yields mastery but brittle intelligence. Poor transfer, limited abstraction, zero adaptability. Imagine trying to ground a particularly unruly child in an open-world playground. They'd just wander aimlessly, utterly overwhelmed. Our characters in this grand AI drama, the researchers, were facing critical limitations. How do you scale environments, handle multimodal perception, manage high-level planning, or even perform low-level control in real-time chaotic 3D worlds? The existing methods were a mess. They struggled with memory too, meaning these digital geniuses forgot what they were doing 5 seconds ago. It's like a perpetually amnesiac toddler, but instead of losing their pacifier, they lose the entire questline. You won't believe the computational burden either. Previous agents couldn't operate under strict latency constraints. It's like trying to win a racing game with a 5-second input lag. You're just gonna crash into everything hilariously. The absurdity of it all. Most commercial games like Genshin Impact don't even have APIs. These AI had to literally stare at a screen and mimic human keyboard and mouse inputs. It's the technological equivalent of teaching a robot to play a game by watching YouTube. It's just overwhelming. These problems meant traditional reinforcement learning was practically impossible for complex commercial games. It's like trying to solve world hunger with a single grain of rice. Can you imagine the frustration? Now, because my continued existence on this platform is fueled by your validation, please take a moment to subscribe, hype, click the little bell icon so you're notified of future disappointments, and leave your feedback in the comments below. Anyway, into this chaotic digital landscape steps Lumine, a 7 billion parameter model, our new contender, they call it. The first open recipe. It's built upon Quendevel 7B Base, a fancy vision language model VLM, meaning it can see and talk. And here, in what they call Figure 1, we have their masterpiece. Lumine's human-like interaction paradigm unifies perception, reasoning, and action in an end-to-end manner. Looks a bit like my nephew's macaroni art outlining a complex process, but I digress. So, how does it work? Well, Lumine processes raw pixels at 5 Hz, which is like watching a slideshow 5 times a second. Then it spits out precise keyboard and mouse actions at a blistering 30 Hz. That's a lot of clicks and movements. It's quite the feat. Think of it like teaching a goldfish to do your taxes. It's an impressive achievement, but you have to wonder about the life choices that led you here. And it uses Genshin Impact as its primary testing ground, of course. Let's dive into the core innovations. Take a look at Figure 3. It's an overview of the Lumine model. It takes pixel inputs, previous actions, and reasoning, then outputs text-based keyboard and mouse actions. A true digital puppeteer. Next, the observation space. Lumine perceives continuous visual input, resizing each frame to 1280x720. They chose this to balance UI, text legibility, and computational efficiency. It's all about seeing what matters and not wasting energy on unnecessary pixels. After that, the hybrid thinking strategy. Check out Table 2. Lumine decides whether to generate an inner monologue using special iThought trust start and iThought turned tokens. Otherwise, it just acts. It's like having an internal dialogue, but only when you really need to strategize. This prevents redundant computation and latency without compromising decision quality. So, it thinks only when its digital brain cells absolutely require it. This reminds me of a time I only thought about doing my laundry when I had no clean socks left. Efficient. Then there's the keyboard and mouse modeling. Forget fancy action heads or vocabulary redefinition. Lumine represents ALK actions as simple text strings. It's surprisingly concise and efficient, avoiding verbose code-like formats. It includes mouse movements, EX, E to I, EZ, and 6 consecutive action chunks for key presses over 200 MIVs, resulting in 30 Hz interaction. Each chunk is 33 MIVs long, meaning it can mimic complex human inputs like holding keys or rapid clicking. See Appendix Table 6, though. It's labeled in the main paper. Each key is a single token, simplifying inference. It's like a secret shorthand language for playing games, allowing precise and subtle movements that would make a seasoned gamer weep. Moving on, the 3-stage training recipe beautifully laid out in Figure 4 and Figure 5. This curriculum is designed to empower Lumine. First, pre-training, then instruction following, finally reasoning. It's like a digital boot camp for a generalist agent. Stage 1 pre-training, 1731 hours of human gameplay data, image action pairs. This teaches it action primitives like picking flowers or basic combat. No expensive human annotations for every single move, it just learns by watching. They mix in about 20% multimodal web data here to keep it generally smart. It's like letting your child watch educational videos, but also a few cat videos to keep them well-rounded. Got to preserve those broad perceptual capabilities. Next, Stage 2 instruction following. 200 hours of instruction following data. This grounds control in language. They used a classifier fine-tuned by human annotations to auto-label data, then GPT 4.1 refined it. The GPT 4.1 part is hilarious. It generates instructions and then acts as a verifier, detecting and discarding mislabeled samples. So, even the AI is questioning the human-generated data. It's like asking a 5-year-old to correct your grammar. Finally, Stage 3 reasoning. 15 hours of human-annotated inner monologues. This enables hybrid thinking for autonomous long-horizon decision-making. They pick Genshin Impact's Act 1 as the training ground. This reasoning data contains 15K traces with an average interval of 3.2 seconds between thoughts. So Lumine learns to think strategically, reflecting on previous behaviors and planning next steps. It's a digital existentialist, constantly contemplating its next move. To ensure consistency over long horizons, Lumine dynamically maintains up to 20 recent steps in context as short-term memory. Previous reasoning steps are preserved as long-term memory. See Figure 6 for the context management strategy. It's a sliding window of consciousness. When new reasoning is generated, the context is flushed and reaccumulated. This prevents infinite memory bloat, which is honestly a problem I wish Mike Brain had a solution for. Then there's the real-time inference optimization. This is crucial for a 7B parameter model. Figure 7 breaks down the latency, and Table 4 shows the inference time at each stage. They needed to get the 200 ms control cycle down. Communication optimization streaming output, so action chunks execute immediately. JPEG compression for images. Persistent TCP connection. It's all about shaving milliseconds because in gaming, every fraction of a second counts. For prefill, they reuse historical KV cache, adopting streaming LLM for efficiency, and attention sync is anchored to the system prompt to prevent collapse. It's like having a digital anchor in a stormy sea of data. Decoding is optimized with a compact action space and draft model-less speculative decoding. Essentially, it guesses the next token, then verifies it. It's like speed reading, but for AI actions. And the infrastructure level optimizations, tensor parallelism across 4 GPUs, W888 quantization, custom GEMM kernels, one-shot all reduce, CUDA graph fusion, GPU offloading for image pre-processing, all just to make this thing. The overall optimization yielded a whopping 3x speedup. The delay before the first action chunk is 110 ms, well under the 200 ms threshold. Even the longest action chunk is only 12 ms, so it's quick. However, it still perceives visual inputs that are 200 ms old, which can be an issue in highly time-sensitive scenarios. It's like playing a fast-paced game with a slight delay. Good enough, but not perfect. And when it does enter thinking mode, latency can exceed 200 ms, creating a brief idle period. But they claim it's so infrequent, you won't notice. It's like your friend pausing mid-sentence to think, but they're usually so quick, you forgive them. So, what did this Frankenstein's monster of code and data actually learn? Let's cut to the chase. Q1, what does Lumine base learn? Turns out it learned a lot during pre-training, even without explicit labels. Figure 9a shows the scaling results. The 7B model consistently had lower loss and better performance than the 2B model. The 2B model even started degrading after 1,200 hours, revealing its limited volume. Some digital brains just can't handle the stress. Figure 9b illustrates the capability emergence of the 7B model. Object interaction, like picking flowers, emerged quickly, under 100 hours. Apparently, digital hands are pretty good at grabbing things early on. Basic combat and GUI manipulation became smooth and reliable around 1,000 hours. So, it can switch characters, chain combos, and click confirm. It's like your teenager finally learning to do chores without breaking everything. For game mechanics, however, were remarkable challenges requiring over 1,800 hours, puzzles, elemental reactions. These sparse occurrences in raw gameplay made them significantly harder. It's like trying to teach complex philosophy from a few scattered notes. Navigation, the most essential component, also took over 1,800 hours. It learns robust road sense, avoiding obstacles, stopping at cliffs, and using gliders. So, after nearly 2,000 hours, it can finally navigate without falling off a digital cliff. Impressive. Now, Q2. How well does Lumine Instruct follow instructions? Figure 10 shows the average success rate on simple tasks. Lumine Instruct non-his, even without history, significantly outperformed all baselines, including GPT-5 and Gemini 2.5 Pro. It achieved over 80% success across all 4 categories: collection, combat, NPC interaction, and puzzle. The biggest gain was in combat, where it doubled the base model's success rate. It's like giving a mildly confused tourist a map, and suddenly they're a master navigator. Figure 11 and Figure 12 further delve into performance on hard and unseen tasks. On hard tasks, Lumine Instruct non-his showed consistent performance in interaction tasks, even with distractions. It still struggled with combat against elite enemies, though. Especially against the eye of the storm on elevated terrain. It would switch to the ranged character Amber, but had limited efficiency and precision in moving target aiming, coupled with delayed evasive actions. It's like bringing a Nerf gun to a real gunfight. For collection tasks also saw a drop, exposing deficiencies in spatial reasoning and fine-grained control for items not on flat ground, and puzzle tasks dropped the most. Turns out, understanding in-game mechanisms is pretty hard for an AI, Who knew? An ablation study in Figure 12 shows that models without pre-training performed worse overall, but hilariously, they did slightly better in NPC interaction. The pre-training data apparently biased Lumine to just pass by NPCs. How rude. On unseen tasks, Figure 12, it still showed strong generalization for NPC interaction. New collectibles, however, were harder, as it had to get close to recognize them. It's like having to sniff every ingredient before you can bake a cake. And combat also declined in unseen tasks, as it was unfamiliar with previously unseen enemy attack patterns. It's like being thrown into a boxing match with an opponent who invents new punches mid-fight. Not ideal. But here's a twist: complex instruction following, Figure 13. Giving Lumine more detailed instructions or breaking down tasks significantly improved its performance. Turns out even advanced AIs need explicit step-by-step guidance, just like us. Now, let's talk about the benefits of history. Figure 14 shows models with multiple historical frames achieved substantially higher performance. The peak was at 10 frames in context. More than that, and performance dropped. Figure 15 compares non-history versus history models. History gave a clear advantage in collection and puzzle tasks. Who would have thought that remembering what just happened would be useful? Revolutionary, I know. Figure 16 gives us the error analysis. Nearly half of all errors were limited multimodal understanding. Agents failed to detect small objects that blended in. History models had fewer such errors, improving dynamic tracking ability. Another major issue: conflicts between language and vision modalities. Lumine would neglect text, overly influenced by vision. It's like seeing a sign that says stop, but your eyes tell you go. Confusion reigns supreme. Non-history models actually made fewer of these modality conflict errors. Apparently, historical context encourages temporal consistency at the expense of single-frame understanding. It's optimizing for flow, not absolute truth. Instruction following was the second major failure mode. Lumine would occasionally abruptly abandon the objective and wander elsewhere. Sounds a lot like my attention span during a long meeting. Spatial understanding errors meant poor navigation and timing issues, and low-level control errors, like delayed key presses, were the smallest portion. But the history model actually made more low-level control errors. Go figure. So, Q3 can Lumine thinking do complex long-horizon tasks? We're talking main storyline missions, hours long. This is the true test of autonomy. It's like finally letting your child go grocery shopping alone. For in-domain performance Mondstadt Act I, Lumine thinking excelled. Figure 17 shows it completed the entire act in 56 minutes, faster than fresh human players' 78 minutes, and comparable to expert human players' 53 minutes. Table 5 confirms thinking models significantly outperformed instruct models. Instruct models often got distracted by shiny objects, puzzles, enemies, and lost track of the main objective. Again, sounds familiar. Thinking models, however, reflect and set appropriate goals, avoiding distractions. One failure occurred when Lumine fell off a platform and failed to generate intermediate reasoning steps to invoke the in-game quest guidance, so it just aimlessly roamed the city. Classic. Non-history models were also heavily affected by the 200 ms asynchronous delay, leading to overshooting the target and difficult GUI interactions. History models with their context performed much more smoothly and stably. Figure 18 details reasoning, quality, error analysis. The history model had an 8.8% error rate, significantly lower than the non-history model's 14%. More efficient, more accurate thinking. Perceptual misrepresentation was the most frequent error. Model describes objects or scenarios that do not exist or misinterprets the character's current status. It's seeing things that aren't there. Digital hallucinations. Premature completion was another type of hallucination, assuming a goal was achieved when it wasn't. Then there's causal misjudgment, wrongly believing an action would achieve an outcome. Oh, Lumine. Self-contradiction occurred, like I closed the task interface before, so I did not close the task interface. It's like watching a debate club full of confused AI. and linguistic collapse in non-history models, where it just spouted gibberish. Yikes. Next, generalization to reasoning OOD missions. Acts 2 and 3 of Mondstadt, tasks it wasn't specifically trained on for reasoning. Lumine completed both acts consecutively within 4.7 hours, expert humans 3.6 hours. Close enough. Figure 19 shows the trajectories. It successfully recognized mechanisms like moving platforms and wind currents in OOD settings. Figure 20 highlights this generalization. It's like teaching a child about one type of dog, and they recognize all dogs. But Lumine's not perfect. Figure 22 illustrates inefficiencies, lack of proactive fast travel, limited minimap understanding, no active health recovery. It's like a child who knows how to walk but forgets that cars exist. It also got distracted by multiple quest markers oscillating between different targets. And it would abandon detours midway, drawn back by the quest marker. Limited memorization, they call it. I call it a toddler in a toy store. Finally, generalization to new games. Figure 23 showcases Lumine in Wuthering Waves, Honkai Star Rail, and Black Myth Wukong. This is the ultimate zero-shot test. Wuthering Waves, a similar genre, saw Lumine complete missions in 107 minutes, fresh humans 101 minutes. It followed guidance, defeated enemies, even leveled up characters. But it mixed up F and E keys, stalling gameplay. And the hallucination Lumine borrows terminology from Genshin Impact. Monsters were hilichurls, the protagonist was Traveler. It's like calling every dog a poodle. Hilarious, but inaccurate. Honkai Star Rail, a turn-based RPG, was a bigger domain gap. Lumine took 7 hours, fresh humans 4.7 hours. It struggled with non-existent jump mechanics, getting stuck against invisible walls. The combat was even harder. It failed to understand targeted skills or confirmation prompts. It eventually had to lower the game's difficulty to win a boss fight. Imagine an AI admitting it needed an easier mode. Well, Black Myth Wukong, a much harder game, was mostly a no-go. It got stuck on invisible walls, misinterpreted scenes as pre-rendered cutscenes, and waited, doing nothing, and it couldn't recognize health bars, so a polite failure there. In conclusion, Lumine shows strong generalization even as game similarity decreases. Core skills can transfer. It's a promising foundation even trained on a single game, a testament to its ability to generalize even if it sometimes needs an easier mode. And since you've made it this far, you're clearly committed. Honor that commitment by subscribing, hyping, ringing the notification bell, and telling me what I got wrong in the comments. It's the circle of life. So, what's the real impact of all this? This AI, with its generalist perception, reasoning, and action capabilities, could autonomously explore game environments. Think about it, an AI that finds bugs and validates quest logic better than any human QA tester. Imagine Lumine identifying inconsistencies in tutorials or interaction design, reducing manual testing costs. It's like hiring a perpetually disgruntled digital employee who's factually good at finding flaws and doesn't demand coffee breaks. And for interactive entertainment, it opens up possibilities for new forms. AI-driven game assistants, streaming where intelligent agents play and comment in real time. Imagine an AI backseat driver, but it's actually correct 90% of the time. Terrifying. It blurs the boundary between player, developer, and audience. Honestly, our technological trajectory is a curious thing. We build complex systems to do things we find tedious, then marvel when they achieve something we thought only humans could. It's just overwhelming. So, they've introduced Lumine, the first open recipe for developing generalist agents capable of completing hours-long complex missions in real time within challenging 3D open-world environments. It adopts a human-like interaction paradigm that unifies perception, reasoning, and action in an end-to-end manner, powered by a vision language model. It processes raw pixels at 5 Hz to produce precise 30 Hz keyboard mouse actions and adaptively invokes reasoning only when necessary. And trained in Genshin Impact, Lumine successfully completes the entire 5-hour Mondstadt main storyline on par with human-level efficiency and follows natural language instructions to perform a broad spectrum of tasks in both 3D open-world exploration and 2D GUI manipulation across collection, combat, puzzle-solving, and NPC interaction. In addition to its in-domain performance, Lumine demonstrates strong zero-shot cross-game generalization. Without any fine-tuning, it accomplishes 100-minute missions in Wuthering Waves in the full 5-hour first chapter of Honkai Star Rail. These promising results highlight Lumine's effectiveness across distinct worlds and interaction dynamics, marking a concrete step toward generalist agents in open-ended environments. So, what do you think? How would you handle your Roomba demanding union rights after it masters complex environmental navigation and recursive reasoning?